In this video, we will do a warm-up question reviewing some of our set operations from section 1.1. So the example says, let U be the set of integers from 1 up to 8. A is going to be the set that contains 1, 3, 5, and 7. And B is the set that contains 5, 6, 7, and 8. And C is the set that contains the elements 2, 6, and 7. And the question says to find, in parentheses, A complement intersected with B. Close that parentheses, and then that whole thing union with C. So I want to give you the opportunity to try this question first. So pause the video for a minute or two to really try this question on your own. 4, 3, 2, 1. Pause the video. Pause it and try this question on your own for 2 minutes. All right, so hopefully you've done that. Hopefully you paused the video for 2 minutes to really try this question on your own. Okay, so let's talk about how we begin. So when we have a series of set operations that we need to evaluate like this, maybe there's multiple set operations, like I have a complement, intersection, and union all in this. If there's parentheses, we should evaluate the stuff inside the parentheses first. Okay, so that's going to tell us what we do first here. But if we were handling something with more, so if there's more than one set of parentheses, then we evaluate the stuff inside the innermost parentheses first. So let me give an example. So e.g., for example, if I had something like A intersected with C, parentheses, union B, parentheses, around that whole thing, and then intersected with B complement. There are two sets of parentheses here. They're the ones around the A intersects C, and those are the innermost ones. So we would do this first. Alrighty, so let's get started with our question now that we know that order of operations stuff. So let me zoom it out a little bit more so I can see you. Okay, so let's begin with getting A complement. So A complement is the stuff in U that is not in A. So those are going to be those even integers like 2, 4, 6, and 8. And that's A complement. Okay, so now I'm going to put an implication arrow. So this arrow, when I write it, this means the word implies. So this implies, and now I'm going to write down what A complement intersected with B is. So I'm going to write A complement, which is 2, 4, 6, and 8. And I need to intersect that with the set B, which is given as 5, 6, 7, 8. And the stuff that's in the intersection is the stuff that's common to both sets. So I can see 8 is common to both sets. Is there anything else? It looks like 6 is common to both sets. And that's it. So I could write that. The stuff that's common is the 6 and the 8. So that is the intersection of A complement and B. Okay, so now I'm going to put another implication arrow. And now I can do A complement intersection with B, the set that I just got, parentheses around that whole thing, and then union that with C. Okay, so this gives me, I know A complement intersected with B is the set that contains 6 and 8, and I'm going to union that with C, and C has 2, 6, and 7. So 2, 6, and 7. So when I union these two things, I have to write any element that's in at least one of these two sets. In other words, any element that's in the set 6, 8, or any element that's in the set 2, 6, 7. Or it could be in both. So that means I'm just going to do this from smallest to largest. Smallest element that's in one of them, at least one of them, is 2, and then I see 6, and then I see 7, and I also see an 8. And those are all the elements that are in either the first set or the second set, or both of them. And that is my answer. So one final comment that I want to make about this and about the implication arrow notation specifically is I use the implication arrow when I want to use what I stated in the previous line to say something else, but when those two things are not equal. Like I had A complement on the previous line, but A complement is not the same thing as A complement intersected with B. I could not just write an equal sign there to connect these two. That's where the implication arrow comes in. It gives us some notation that we can use that makes sense. All right, so in terms of our goals for this section, we have finished our first goal, which was doing a review problem from section 1.1. In the next video, we'll talk about how we can represent set operations visually using Venn diagrams.